Hi everybody, today I want to talk to you about inverses for linear functions. So this is an intro for how to take a inverse of any linear function, and I'm going to use the function today y equals 2/5 x plus 2, and that is also in function notation. I'm going to be referring to f of x quite a bit, and that's the same as setting it equal to y. So I have a line. It's got a intercept of +2 and has a slope of 2/5. So I'm going to go ahead and draw that line right there. So there's my line. And I usually don't plug in points, but points are quite nice when you're looking at an inverse and if you've never taken an inverse of a function before. So here are some points that I just chose that are easy to plug into this function. That's going to give me nice whole numbers. So for example, if I plug in a 5, I'm going to get out a 4. If I plug in a 0, I'm going to get out a 2. And so we're all good at graphing lines. And so let's talk about getting an inverse function. So we know what happens to values when we plug in an x, we get out a y, but an inverse function essentially undoes what the original function does. So for example, when we plugged in a 10, we got out a 6. Well, what is the function that would do the inverse of that? So for example, if I took a 6 and plugged it in, how would I get out a 10? So we're going to call that f inverse. And so there's f, and it looks like a little to the -1, but it actually just means f inverse. So whatever function you had, f inverse undoes that f function. Okay, and we can think about, okay, what would be a function that would like do the opposite order of the f function? So if I took 10 and I plugged it into the original function, the first thing I'd do to it is to multiply it by 2/5, and then I'd add 2 to it. So if I wanted to undo that, maybe I'd have to do it in the opposite order. So maybe the first thing I do is I take x and I subtract the 2, and then I multiply by 5/2 instead of multiplying by 2/5. So this essentially undoes the order of the original function, and we call that f inverse. And we can also set it equal to y instead and just look at the line of it. So for example, if we took a 6 and we plug that into f inverse now, 6 minus 2, that's going to be 4, and then times 5/2, that's going to be 10. So yes, that works. And let's go ahead and let's take a look at each point. So if I plug in 0 into this new function, I should get out a -5. And if I plug in these subsequent points, I should get out all of that. And if any point this is too fast, you can always stop while you're taking notes and pause and try this. All right, so here's my new points, and I'm going to plot them and I'm going to graph them. I'm going to look to see what this line looks like. We know it's going to be a linear function, and so we'll plot these points and look at that. So this new function also is a line, and notice it has a positive slope as well. So my original function had a positive slope, and the inverse function still has a positive slope. So a lot of people think that if I take the inverse of a function, I'm going to get like the opposite slope or a negative slope. No, I still get a positive slope, but these lines are very much related. First of all, they're related because every single point xy is switched. But if you take a look at this line, which I drew in blue, that's y equals x. That's a 45-degree line. And if you held your paper on y equals x and you rotated, you would get one or the other function. So if you rotated that green line across the y equals x, you would get that yellow function. So every single inverse is a flip on the y equals x or a rotate on the y equals x of the original graph. So that's kind of interesting. So if you take any graph and reflect on y equals x, you always get an inverse. So that's kind of an interesting idea. And then the second idea is that if you switched all the points xy on the original graph, you would get yx to get the inverse graph. Because I know sometimes it's a struggle trying to graph inverse functions, especially if they get more complicated than lines. Take every point and switch each of the points. So that's kind of a tip that I wanted to give you. But as the as the functions get harder, because we'll be taking inverses of functions that aren't always easy linear functions, we want to be able to do this algebraically too, without just guessing at it. So next, let's talk a little bit about getting an inverse algebraically. Okay, so one major tip for us is that if you take the original function, since all of the x, y points switch, we might as well switch all of the x's and y's. So write the original function and then switch all of the x's and y's. Now, if the function's super complicated, you could leave it in this form, but a lot of people like to solve it so that it's solved for y, so you can write it as f inverse. And that's what we're going to do here. We're going to go ahead and rewrite this. We're going to set everything equal to y. So we'll just subtract 2, and then we'll multiply it on both sides times 5/2, and now notice that is our f of x function. So really nice and simple. If ever you want to take the inverse algebraically, switch the x's and y's, and again, solve for y if you can. So there's my inverse function, and you don't even have to guess at it. So a couple ideas about inverses and their function. So let me bring it back to this original function. In the original y function, if you plugged in 0, you got out 2. In the inverse function, if you plugged in 2, you got out 0. And we talked about that in the previous screen, because the point 0, 2 and the point 2, 0 are on the subsequent graphs. So one big idea is if you put the inverse function inside of the f function, they're supposed to undo each other. So for example, if working from inside out, if you took f inverse of 2, f inverse of 2 is going to give you 0. And then if you took f of 0, that's supposed to give you 2. So it looks like f and f inverse cancel each other out, and you just get what's inside, and that is true. And that's also true if you do it the other way as well. If you took f inverse of f of 0, if you look inside first, f of 0 is going to give you 2, and then f inverse of 2 is going to give you 0, and again, those guys cancel each other out. And so that's a big idea for us. In fact, that's a rule. And so our rule is two functions are inverses of each other only if and only if, f of g of x gives you x and g of f of x gives you x. So they will cancel each other out both ways. And you have to try them both ways, because if they only work one way and they don't work the other way, then they're not truly inverses of each other. But that's one way that you can check algebraically if two functions are inverses of each other. So let me go ahead and give you an example of our algebraic function. So right now I've written on the outside of the function the original f function, and I left an empty space, and now I'm going to plug in the f inverse function. So there's f inverse, and then if we do a little algebra, like we distribute that 2/5 across, then we simplify and we get x. So notice f and f inverse, they cancel each other out, and now I also have to try it the other way just to verify or prove. Okay? So I'm taking the f inverse function and I'm writing that on the outside, and inside of it I'm going to plug in the f of x function, and again a little distribution, and those guys cancel each other out as well. And so that's the big idea of f and f inverse. So excellent job. If you have any questions, please leave me a note or email me. If you have any suggestions, or you would like to see some other math done, please let me know. Okay, have a great day.